In this lesson, we'll be looking at exponential growth and decay problems, basically word problems. Now I have here an exponential equation, f of x equals a times b to the power of x. Now, there's not going to be any other transformations happening to this exponential equation, just the a value and then an exponent of x. Now, what all this will represent, f of x will represent the final amount of whatever we're finding. A represents the initial amount. So, if we start with a population of 10,000 people, or if we start with $5,000 in our bank account, that sort of thing. So that's what our A value is. Now, our B value is the base with the exponent. This is going to represent 1 plus the growth rate, or 1 minus the decay rate. And the rate will be as a decimal. I'll be showing you in the first example why we do 1 plus for growth or 1 minus for decay. Now, very important as well, the exponent x is the number of growth or decay periods. So it's not necessarily going to be how much time is going by, but it's going to be the number of growth or decay periods. So once we look at the first example, it'll be a little more clear for you. A population of bacteria grows at a rate of 22% per day. Okay, so this is growing at a rate of 22% per day. If the population is currently 500 cells, how many will there be after 5 days? Now, what I'm going to do, I'm going to use not f of x, I'm going to use a letter that kind of makes sense. If we're finding population of bacteria, I'm going to use p of x. Now, I'm not going to be putting anything in here for the brackets. I'm not going to be putting x for now because we're actually going to be evaluating for a value of x. Now, my initial value, I'm starting with 500 cells, bacteria cells. If I wanted to increase it by 22%, now you may remember from back in grade 9, to find 22% of 500, we can multiply by 0.22. Now, that would only find what is 22% of 500. It's not going to add the 22% for us. So what we have to think of, and this is the reason why it's 1 plus the rate if we are growing, we are adding 22% to 100%. Now, 100% as a decimal is 1, so 1 plus 0.22 will add the 22% for us. So that's why it's 1 plus the growth rate. Now, why do we have an exponent? Think about it this way. What I've done right here is I'm adding 22% once. If I want another year to go by, I would multiply by, now that would be 1.22 for the second year, and multiply by 1.22 for the third year, and so on. Now, a shorter way of doing this, I have 1, 2, 3 1.22s multiplying each other. So what's a quicker way of doing that? Using exponent. Now, I'm not doing it 3 times, I'm doing it 5 times for this problem. Now, this will bring me back to my original notation. What I've done here, instead of having x for a formula, I have the value of 5. So what we've done here, we're evaluating p of 5. So all I have to do is type this into my calculator to get it, and I get an answer of 1,351.35. Now, in terms of rounding, we'll use our common sense here. I don't think we can have 0.4 of a cell, so I'm going to round to the nearest whole number. But one thing I'm going to do, I'm going to put a dot over my equal sign, which means it is approximately 1,351. I'm also going to write out a therefore statement. So after 5 days, there will be 1,351 cells. Question number 2 we'll do in class. Now this is actually going to be another exponential growth problem, so we'll look at it in class. There is a little bit of a trick to it though. Let's look at question number 3. A town's population is currently 250,000. It's expected to decrease by 2% per year. What will the town's population be in 15 years? Now this time I'm going to write off to the side. Now that we know what the formula looks like, I'm going to write out what the A value is. It's 250,000. Now what about the B value? Now this will be the base of the power. Last time we took 100% and we added 0.22. Now, that was because we were increasing by 22%. This time we were actually decreasing by 2%. So what I want to do, actually, I want to take away the 0.02 and get 0.98. Now what this tells me is that each year I will have 98% of the previous year's population because I'm taking away 2%. Now the x value will be after 15 years are going by, and it is per year decreasing, so x will be 15. Now this is not really necessary to do, but some people like to do it just to organize their thoughts. Now we're talking about population again, so I'll use P of, and I know that I'm going to be applying the exponent 15 times. So 250,000 times 0.98 to the power of 15. And again, all we have to do is just calculate this, and I get 184,642. Now it's 0.27, so this is going to be rounded, and I'm not going to have any decimals because you can't have 0.3 of a person. And I'm going to put in my units here is people. And I have my therefore statement. So there's one example of exponential growth, and this one was exponential decay. We'll take a look in class on Monday, a few more difficult problems.